Bismillah ar-Rahman ar-Rahim. Today, inshallah, we're going to cover chapter 4, which is like a continuation for the previous chapter, chapter 3. But in chapter 3, we were only dealing with discrete random variables and discrete probability distributions. Now we're going to deal with continuous random variables and probability distributions. So, what is a continuous random variable and why is it useful and why do we need to learn it since we have already learned the discrete counterpart? Well, a continuous random variable is a random variable that takes continuous values which could be presented in an interval. What can be an example of that? What are these values that would be presented in an interval? Well, they are the continuous values like time, like length, like area, like volume, like density. All of these are continuous values that could be presented using a continuous random variable. In the previous chapter, we didn't deal with anything that has to do with time, at least not to my memory, except if we have done something of the sort in the Poisson. But now we're going to be dealing with time and space and all of these continuous values as how we're supposed to deal with them. So, continuous random variables, an example of it might be letting capital Y be the height of a person. This is a continuous measurement. Letting capital X be the volume of a juice can, or letting Y be the waiting time until the next person arrives at the server. So these three things, we have not dealt with them in continuous and discrete random variables. Now we're going to deal with them using the continuous random variable. So for the discrete random variable, we had something called probability mass function. We're going to have something similar for the continuous random variable, which is the probability density function, or PDF for short. And this PDF has some properties that need to be met in order to say that, okay, this function is a probability density function. So, for a continuous random variable, capital X, a probability density function is a function such that the first property we're going to have is the non-negativity constraints, or the non-negativity property, where all of the values coming out of this probability density function being greater or equal to 0, they are non-negative. And the reason behind that, we explained it in the previous chapter, is because these functions provide us with probabilities, and probabilities can never be negative. So this is the reason behind this one. The next one, when you integrate this function from minus infinity up to infinity, you get 1. This reminds us of a property we've seen for the probability mass function. When we sum all of the probabilities for all of the outcomes, we get 1 also. So is it the same? Yes, it is exactly the same. But here's the thing I would like to bring your attention to. Here it tells us to integrate from minus infinity up to infinity. However, not all probability density functions go down to minus infinity and up to infinity. Some of them go from 0 to infinity. Some of them go from minus infinity to 4. Some of them go from 0 to 1. So this just simply means, this notation is a generalization, and all it means is that when you integrate from the lowest outcome to the highest outcome you have inside of your continuous probability distribution for a continuous random variable, and you integrate this function here, you get 1. This is all that it means, okay? And we're going to see this generalization a lot in the formulas we're going to be provided. I'm going to bring your attention to it whenever I see it, okay? So you're going to get bored of me notifying you about this, so don't worry. The next one, when you want to find the outcome of A to B, or the outcome from A to B, you just have to integrate the probability density function, or the PDF, from A to B. And with this, you end up with the probability from A to B. The thing is, we know that when we integrate over a certain function, we are finding the area under that function. So, does this mean that probabilities are the area under the probability density function? Yes, exactly. So, the area under the function, the PDF, in that region is going to be our probability of these two outcomes. So, this is mainly it. The next one. The probability of capital X equals 0. Well, this sounds strange. We in the previous chapter we have dealt with a lot of these guys, and they rarely, or like they never even got to have a value of 0. So why is this the case here? Why in the continuous random variable or in the probability density function we cannot have exact outcome, the probabilities for exact outcomes. The reason behind this comes to the previous property here, is when you have an equal sign here, you're integrating over the same region. So let's say you're trying to find the probability of x equals 4. You're going to be integrating the probability density function from 4 up to 4. So when you integrate over the same region, how much you get? You get 0. The reason behind this also because you're integrating over the same region, you're getting only a line. You don't get an area. So the area of a line is 0. So yeah, all of this comes back to why this equals 0 here. The last one means that the equal sign inside of an inequality or in an inequality doesn't matter anymore. Does not change the final answer. I'm sorry, it matters, but it does not change the final answer. So if you have the probability of x greater than 2 and the probability of x greater than or equal to, they're going to give you the same final answer. Both of them are equivalent. And here you can see the number of combinations you can change these inequalities and still would give you the same answer. All of them are equal. But here's the thing I would like to bring your attention to also here. When I was taking the course, my instructor told me, and I'm going to give you an example to explain the idea to you because I don't clearly remember exactly what he said. But the idea behind it was, if you had a question that told you to find the probability of something finishing in at least 5 minutes, we know that at least 5 minutes is x greater than or equal 5 minutes. But you might say, well, because of this property, I'm going to say probability of x greater than 5 minutes. I don't need to put the equal sign. The thing is, you might have marks deducted from you because your expression that you are solving for does not match the statement provided in the question. So this was the case when I was taking the course, or at least that's what I understood. Refer to your instructor to see whether it still applies or not, to be on the safe side. Now let's solve some questions regarding that so we can understand these ideas better. Here is our f of x, or our PDF, the probability density function, and here is the domain of x. The domain of x here is x greater than 0, which is 0 from 0 to infinity. So keep this in mind, we're definitely going to use it. So we have all of these parts of the question here laid for us, and we're going to solve the first one. The first one tells you probability of 1 less than capital X. Well, you can say probability of x greater than 1. You know, just trying to flip them around and trick you. It's just the same. Probability of x greater than 1. So how do we solve it? Well, probability of x greater than 1. So we need to find the area from 1 and up to infinity, where x is from 1 up to infinity, or x is greater than 1. So integrate from 1 up to infinity, and you're going to end up with the answer here. I'm not going to go into the integration because it's going to take time and it's unnecessary. I'm just going to explain the statistical ideas here. So the next one, we want to find the probability from 1 to 2.5 for capital X. So how do we do it? Remember the property we saw. We integrate over this region. But here is a thing, a trick they might do in the question. Say that the region here, the domain of x goes from 0 up to infinity. They might put, instead of 1, they put -1. So are you going to integrate from -1 to 2.5? This is going to be incorrect. You integrate from the lowest value you have, which is 0. Your domain does not go down to -1. So you're going to go to the lowest your domain go and integrate to the highest your domain go. So in this case, all of these numbers are within the region, so we have nothing to worry about. So we're going to straightforward integrate from 1 to 2.5, and we should end up with this answer here. The next one, integrating from integrating probability of x less than 4. So in this case, we're gonna take 4 and everything below it. But in this case, our domain does not go down to -infinity. It only goes down to 0. So we're gonna integrate from 0 up to 4. So in this case, we should end up with this answer here. Next one, probability of x equals 3. Recall the property that we talked about. This equals 0. Why? Because here we are integrating over the same regions and it equals 0. Next one has nothing new about it, just they flipped it like they flipped the first one here. So you're going to be solving x greater than or equal 3, integrating from 3 to the highest we have, which is infinity here, and you're going to end up with the answer at the end. Now, we have another part of the question, which is x such that the probability of capital X greater than small x equals 0.1. The idea behind this question is quite simple. They just want you to find the value of x such that if you put it inside of this expression, the probability gonna give you is 1. So let's solve it. Capital X greater than x, which means that you're gonna try to find the area from x, the one you don't know, up to infinity, because you have capital X greater than x. You're gonna go from x, whatever greater than x. Our domain of x here goes to infinity. So in this case, we're gonna be solving something of this sort, like this. This is the integration we have to solve. So after we solve it, remember that we want to try to make it equal 0.1 here. And when we make it 0.1 with some algebraic manipulation, we can end up with the final answer here. You can practice it. Here's an example for you to practice, and here's the answer for it if you want. Yani. Now, the cumulative distribution function, or CDF for short, it is the same exact concept from the previous chapter, but now we have some add-ons on it. We have some additional information to understand in order to use it. And here in this chapter, it is absolutely crucial. I'm going to be solving everything using the cumulative distribution function. Everything. Almost everything. So, let's see. The cumulative distribution function, it has the same notation, capital F of x, and the probability of capital X less than or equal small x. Remember the last property? We can also say that probability of capital X less than small x also cumulative because of the property, remember? Here is the formula for it. Here is the formula. And here it tells you to integrate from minus infinity. Remember, this is not minus infinity necessarily. It just tells you to integrate from the lowest value you have, whether it is minus infinity, 0, minus 1, 4, whatever it is, from the lowest value to x. And you're going to end up with a function that you can plug any number in it, or any number in the domain of x, let's say, and it will give you the probability of it, the cumulative probability of it. We're going to see how we're going to use it, don't worry. Here, and there's a nice relationship between the cumulative distribution function and the probability density function between CDF and PDF. When we integrate PDF, we get CDF. So when we derive CDF, we also get PDF. So this is the relationship between them. May be useful for you. I don't know. Maybe you get a question in the homework that requires this idea. I don't know. But use it to your advantage. Now we're going to be solving a question regarding it. So this is the cumulative distribution function. It's not going to look as ugly as this one, but you have to understand what this one look like, why this one look like this, and you have to understand how to read it. So here you're going to have the outcomes. Here are the outcomes, okay? And to the left of the outcome of each outcome is the probability of that outcome. So the probability of any outcome that falls into this range is going to be 0. Anyone that falls into this range is going to be this formula here, or this function here. And anything that falls into this range is going to be this one here. By the way, the one in the middle is going to be your domain of x. These guys are out of the domain, or the domain of x or range, whatever you would like to call it. So let's see our questions. And for the questions, all the questions must be in the cumulative expressions, or else you will not be able to use this function here. So go to the first part of the question, part A, find the cumulative probability for 1.8. And why did I say cumulative? Because, although this one does not have an equal sign, because of the property we just seen. It does not need to have an equal sign anymore to be considered cumulative. As long as it less than or equal is going to be cumulative. So 1.8 is a cumulative expression. So this one is probability of x less than 1.8 is a cumulative expression. So how do we solve it? This is our outcome. It is cumulative. We look into the these ranges or these domains. Where does it belong here? Well, it belongs between -2 and 2. What is its probability? Well, its probability is given as this formula here. So once we plug 1.8 inside of this formula, it should give us the probability, the cumulative probability for 1.8. Next one. The probability of x greater than -1.5. Is it cumulative? No, it is not. We have to make it cumulative. How? Using the complement method. So after we've done this, here is the cumulative expression. Now we can use the cumulative distribution function to solve it. So the probability of x less than minus 1.5. Where does minus 1.5 belong inside of our CDF? It belongs here. So since it's belong here, here is its probability. This is its probability. Just substitute minus 1.5 instead of x inside of this function here, and you should end up with the answer here. Next one, probability of x less than minus 2. Probability of x, where does minus 2 belong? It belongs here. So it's given with this function here, and once we solve it, we should end up with the answer, which is 0. Next one, which has a really important idea. I would like to take my time explaining it. The probability of x going from minus 1 to 1. Well, one of them is cumulative and the other is not cumulative. How do we deal with this one? The thing is, there is a nice property that we can use, that if you want to solve an expression like this, you can take the cumulative of this part of 1, the cumulative of 1, the second one, and subtract it from the cumulative of this one. So we're going to have the cumulative of 1 minus the cumulative of minus 1, and this should be equivalent to this expression. Here, I have written it here, and I have put the absolute values because we are dealing with probabilities. We always should get a positive number, non-negative number. I'm sorry, we always should get a non-negative number. So I can get away with putting the absolute value here. But the thing is, the real rule is to subtract to subtract the cumulative of the bigger number from the cumulative of the smaller number, and you should end up with the answer for it. Now we can solve each one of these by itself, and we should end up with the answer for this question, which is 0.5. Yep, the expected value and variance. Well, for the expected value and variance, they are practically the same idea from the previous chapter, but we have different formulas to use them. It have the same notation, E of x or mu for the mean, and here is going to be the formula for it. Remember, from minus infinity up to infinity. It does not necessarily mean that you're going to integrate from minus infinity up to infinity. From the lowest up to the highest outcome you have in the domain of x. So this is it for the expected value. We're going to solve a question on it. For the variance, denoted with the same thing from the previous chapter, and have this formula here. The same thing that went here is going to go here. This does not necessarily mean minus infinity, just means the lowest outcome. This does not mean infinity, it means the highest outcome. I'm getting tired of saying it. Just don't fall into the trick. خلاص يعني ما يبغى لها شيء سهل. So let's solve some questions on the expected value and variance. Here we're going to have a PDF, probability density function, which is this one. And we have the domain of x going from 0 to 4, not minus infinity, not infinity. So it just goes from 0 to 4. Don't fall into the trick. خلاص. So determine the mean and the variance. Very simple. Let's have the formulas because we're definitely going to use them. So we have to integrate for the expected value first. We have to integrate from the lowest outcome to the highest outcome. We have to integrate this function and multiply it by an additional x. So multiply this by x and integrate it from 0 up to 4. You should end up with the answer here at the end. The next one, the variance. The variance, same idea, but instead of multiplying the f of x by x, now you're going to end up multiplying it by x squared, and at the end you're going to subtract the mean squared. So you should end up with this answer here. Okay, very nice. Now, the expected value for a function of continuous random variable. Remember this one? Like maybe, for example, you don't want to find the expected value of x, you want to find the expected value of x squared, or x raised to power 3, or 8x, or 7 minus 8x, or something like this, something convoluted like that. Here's a function for you in order to find all of these expected values. So we're going to have the same function from the previous question, and we're going to have this h of x, which is 8x raised to power 3. So let's see the function. What does the function tell us? Tell us to multiply h of x by f of x and integrate from the lowest value, not minus infinity, the lowest value up to the highest value from 0 to 4. And here you should end up with the answer, hopefully. Yep. Now we're going to go, okay, we got here fast. Now we're going to get into the core of this chapter, the common continuous distributions. Previously we had common discrete, now we're going to have common continuous, which is going to be technically the hardest part of the chapter. We're going to have all of these to talk about and to discuss as much as we can. And we have these things, and I would like you to identify these things. So these are the distributions we're going to be talking about: continuous, uniform, normal, exponential. And here are the things I want you to understand from each of these. You have to know the probability density function. You have to know the cumulative distribution function. You have to know the formula for the mean and for the variance. Okay? I'm going to provide everything for you, and I'm going to try to explain each and every one of these to my capabilities. So the first distribution we're going to be talking about is the continuous uniform distribution. We remember that we took the discrete uniform distribution previously, or in the previous chapter. Now we're going to be talking about its continuous counterpart. So we have these few things to talk about. So the first thing we're going to be talking about is the probability density function, or the PDF for it. And the PDF looks like this, okay? 1 over b minus a, where a is the outcome with the smallest number, quite similar to what we used to have in the discrete uniform distribution, and b is also the outcome with the largest number, exactly the same as we had in the discrete uniform distribution. The domain of x goes from a to b in this case. So now we're going to be talking about the cumulative distribution function, or the CDF, which is, in my opinion, the most important part. So the CDF looks like this, looks like a piecewise function, يعني معادلة من طابقين ثلاث طوابق حقيقة يعني، بس it's quite easy to read. What the first line just talks about whatever value that is less than the smallest outcome we have. So maybe your outcome goes from 1 to 4, where 1 is A and 4 is B. So whatever less than 1 is going to be included in here, and its cumulative is going to be 0 naturally. And whatever is greater than b, which is 4 in our case, maybe you want to cumulative 410. Cumulative 410 is going to equal 1. So this middle part is what we gonna really care about. And you're gonna, يعني, if you are in an exam setting, unless you are told to write this whole thing, if you're just solving for the continuous uniform, you're gonna be using this one here, this small formula here. So yeah, this is primarily what we're going to care about, and we're going to see how we can use it in solving. Remember, cumulative only works for cumulative expression. So lastly, we have the mean and variance. Not much to be said about them. Like, it's good to have them around. There is nothing new. Just implement the formulas right away. Now let's solve a question. And the question says, suppose that capital X has a continuous uniform distribution over the interval 1.5 and 5.5. Determine the following. Well, 1.5, 5.5 is the domain of X here, where A is 1.5 and B is 5.5. So let's solve the first part of the question. Of course, we're going to need this one there. So the first part of the question tells us to find the probability of X less than 2.5. So whatever less than 2.5, so we go to our domain to see the 2.5, and what is less than it? What is less than it? The smallest outcome we have is 1.5. You cannot go down to minus infinity because our domain stops at 1.5. So you integrate the probability density function over 1.5 to 2.5. So it's going to look like this. So this is the integral you're going to be solving, and this is the answer you're going to get at the end. By the way, this is unnecessarily difficult or unnecessary work, let's say, and we're going to see how we can use the cumulative to solve this one like this. So now we're going to find the mean, variance, standard deviation. So we're going to need the formula for these guys, and the formulas have A and B in them, and we already found A and B, so let's put them there. So A and B, now let's find the expected value, and the expected value is just by implementing the formula for the expected value, and it's this one there, and the variance is by implementing the formula for the variance, and lastly the standard deviation. Take the square root of the variance and you're going to end up with the standard deviation. Very easy, extremely easy. So now we're going to see how we can use the cumulative distribution function to solve. But first, we need to learn how to do it, because maybe in the exam you will be asked to produce the cumulative distribution function, and I don't think it's given. Actually, maybe it's given, maybe, I don't quite remember if it's given in the formula sheet, but here is the formula because we're going to use it. And how do we utilize it? Well, we have A, B, we have everything we need. Here is A and here is B. All we need is A or B. So we should produce a cumulative function that looks like this, hopefully. Now, remember the question we just solved? The first one, this one. I told you we can solve it in an easier way. So this 2.5 falls in the domain of x. So we can use this formula on it. So when we use this formula, how much should we get? Well, substitute 2.5 in x here. Since this is a cumulative expression, we can just straightforward substitute 2.5 or the outcome inside of the function, and we should end up with the same answer that we ended up previously with, which is quarter, same as the previous slide. Now let's solve a conceptual question about continuous uniform distribution. So the question says, the thickness of a flange on an aircraft component is uniformly distributed. So they told us the distribution in the question between 0.95 and 1.05 millimeters. Determine the following. So let's see the following that we need to determine. The proportion of flanges that exceeds 1.02 millimeters. So it wants the fraction of these flanges, or whatever this is, that has a thickness that exceeds this number there, 1.02 millimeters. So the expression we need to solve for is going to be the probability of x greater than, well, exceeds 1.02. So this is this is A, this is B, and this is the expression we need to solve. So the thing is, you can solve it using the integral. You can solve it using the cumulative function that I have just showed you. I'm going to solve it using the cumulative function. So let's put the cumulative function because I hate integration. I don't need to integrate. And since we have found A to be 0.9 because it told us that it falls between 0.9 and 0.05. So this is the domain of x here. The values don't get lower, don't get higher. So this is my A, 0.95, B, 1.05. So with all of this, I can solve this one, but this one is not a cumulative. We have to change it, make it cumulative. How? Just take the complement of it. Well, after we took the complement, now we can solve it using that formula. After we did that, we just implement the formula and we get the answer at the end. Now, next question. The thickness exceeded by 90% of the flanges. Okay. So here it wants the thickness, or the thickness for these flanges that are exceeded by 90%. So 90% of the thicknesses exceeding it. I want the bottom 10% because 90% are better than it, exceeded it. The remaining is going to be the bottom 10%. So I want to find, of course, A and B, I want to find this expression. If it's exceeded by 90%, then it's going to be the bottom 10%. Okay? Hopefully it is clear. Inshallah it is clear. How do we solve a question like this? Well, this is the cumulative here. This is a cumulative expression. So we can use the formula and substitute x with x. Keep x as it is. Put B, put A, and then equate it to 0.1. It's going to look like this. Solve this one. Extremely easy to solve. And you're going to end up with the answer at the end, inshallah. Now, next question. The next question about the mean variance of flange thickness. Just implement right away. We have the formulas. We have everything we need. Just implement the formulas. We know A, we know B. Just straightforward. This is everything. Okay. The normal distribution, which is the most important distribution we're going to take in this course or at any other course you might take. The normal distribution is the most famous, this according to the book, the most famous distribution. And it's the most crucial for an engineer to know. To know the magnitude of how important it is, I tried to leave nothing uncovered regarding the normal distribution in the slides, where on average, each distribution gets about, I don't know, 4, 6, 5 slides, maybe an average of 6 slides or something. This one got 27. So this is how important it is. I tried to cover almost everything there. So yeah, let's begin. The normal distribution. The probability density function for the normal distribution is this one. It looks quite horrendous, and lucky you or lucky us, we don't need to integrate it nor to deal with it whatsoever. Just look at it, know the parameters into it, and you're good to go. The parameters here are the sigma and the the mu. The sigma and the mu, the mean and the standard deviation. So the mean and the standard deviation are the parameters in this. If you change one, the distribution changes. If you change the other, the distribution changes. So this is it. However, since we're not going to be integrating this one or not going to be dealing with it whatsoever, how are we going to solve it? Well, of course, using the cumulative distribution function, right? Kinda. We don't actually have a function. We have a table. Okay, here's, oh, by the way, the domain of x, I forgot it, I'm sorry. We're going to be having a table to solve the normal distribution, where the table is going to be at these pages. It's actually one long table that extends over 2 pages, but you know, this is it. One is for the negative numbers and one for the positive number, and we're going to see what all of this means later. Don't worry about it. The mean and the variance, just I put them for the symmetry of the slides. You are going to be given the mean and the standard deviation in the question, so I just put them for you know, for aesthetic purposes or something like this, whatever. Now, there are going to be some important focal points that we need to focus on in order to understand the normal distribution well. The first thing and the most crucial, actually one of the most, I'm going to say crucial a lot, or important, because you know, yeah, it's important within important within important, whatever. The first thing we're going to be talking about is standardization, or the standardized normal distribution, which is, if you want me to put it between 2 brackets, the first step you will ever do whenever you're solving normal distribution. This is the first step you always do, okay? The second part, I'm going to be talking about visualizing the normal distribution, then evaluating the normal distribution. Well, we've said we're going to we're evaluating it using a table. So here we're going to learn how to use the table and how to pull some of the tricks they might pull on us, and how to you know how to deal with them. Next, we're going to know how to find a p for a certain value of z, or finding a z for a certain value of p. We're going to see what all of this means later. And at the end, we're going to get inclusive problems that will include everything here, so you can at the end get a really good foundation into for the normal distribution. So let's talk first about the standardized normal, or as I have earlier mentioned, the first step you will ever do whenever you see this question follows a normal distribution. This is the first step you always do. You standardize. What is standardization? Well, a standardized normal distribution is a special case of the normal distribution. Naturally, it is a normal distribution, but it's a special case. What is special about it? The parameters. We have mu to be 0 and sigma to equal 1. This is how it looks like. So, if we have a distribution that does not have these parameters, we can force it to have them. If it has a mean of million or standard deviation of 7 billion, we can force it to be 0 and the standard deviation to be 1. How? We're gonna see. However, the standard normal, or the standardized normal distribution, have a special random variable, which is capital Z. This is the random variable for the standardized normal. Whenever you see capital Z in the book, this means that the distribution or the random variable is already standardized, okay? And it also gets a different notation for the cumulative distribution. So it's the cumulative expression is denoted instead of capital F of X for the normal ones, not normal distribution one. The previous distribution we took, here we're gonna have capital Phi of Z. So these are the notations that you may see in the book. Now, how to standardize? How to force everything to follow these conditions here? Well, we do it by this formula here, where we take the outcome we want to standardize, or the distribution that we want to standardize, we subtract its mean, the mean of the distribution x, and we divide it by its standard deviation. We're going to have enough practice on how to do that, so don't worry, you're not going to be having gaps in this idea. So here, how we can standardize the normal distribution. We're going to have this normal distribution with mean 5. Of course, we are always given the mean in the question, and the standard deviation of 2. Let's put the formula, or the equation that we're going to use, and let's put the parameters that we are going to need, because see, we need mu and we need sigma in this equation. Let's see the let's see the following distribution that we need to make to standardize. So the first one, probability of x less than or equal to 1. So what do? We take the outcome 1, we subtract its mean from it, and we divide it by its standard deviation. Not variance, standard deviation. This is a common mistake, okay? So it's gonna look like this at the end, and you may end up with, you will end up with this one, of course, inshallah. Yes, yes, of course. So next one, the probability of x less than or equal 15. How do we do it? Same exact procedure. Subtract this from the mean, divide it by its standard deviation, you should end up with the answer. The next one, the probability of x greater than or equal 7.5. So previous ones were less than, this is greater than. Does this make a difference? No, it does not. We're going to do the exact same procedure. There is no trick about this here. It's do the exact same procedure. Take 7.5, subtract it from the mean, divide it by its standard deviation, you're going to end up with the answer for this one too. Here is a question for you to practice. And of course, the last one is solved the same way. Here is an example for you to practice. It has a trick. I don't know why I'm telling you, but it has a trick. And here are the parameters that you're going to use. Here are the solutions. So, standardize and see if you get these answers at the end. And by the way, if I get a mistake in the slides, please correct me down in the comments. I'm not infallible. And these examples I have invented, so there's not really a solution manual for them. So if I got something by mistake, correct me. It's okay. Now we're going to be talking about visualizing the normal distribution. Well, as we have seen in a couple of slides before, that the normal distribution has a bell curve. And this bell curve has a nice property that we're going to use, which is perfect symmetry. So this bell curve is perfectly symmetrical. Let's take an expression and demonstrate why this could be beneficial for us. So let's take this expression and plot it. So the probability of z less than or equal to is the area from 2 and down to infinity. So since this curve is perfectly symmetrical, can we say that this area from 2 down to infinity is equivalent to the area of -2 above to infinity? Is it the same? Can we say that? Is it safe to say it? Yes, it is absolutely safe to say it, as we can see here. So this expression, probability of z greater than or equal -2, and this expression here, they are both equivalent, and we can substitute with one in place of the other. It is absolutely fine, and we're definitely going to use this property when solving questions. Here is a thing, but just as you can see, there is an x here. This is because of the graphing calculator that I have used. But it should have been like z in here, like it should, instead of x should be z. So it's just a minor mistake because of the calculator I wanted to highlight. So a different example could be for 1, for example. So probability of z less than or equal 1 is going to be the same probability of z greater than or equal -1. So it's demonstrated here better than me saying it. And here are different cases for different, visualizations for different cases. So this expression may be like this is from the book, and this is a different visualization for a different expression. By the way, for this case, I don't know if this is going to allow, but if you go from 0 to -1, and you calculate this area and you multiply it by 2, it gives you the entire area over this bound here. So yeah, these are some nice properties. We're going to be talking about them in the next slide. So for evaluating the normal distribution, I have told you that we're not going to be using the formula, we're going to be using a table. And I have told you that this table is quite long and extends over 2 pages. This table has a table for positive numbers, positive values of z rather, and positive and negative values of z. So let's say we want to evaluate this expression. And by the way, it is already standardized. If it was not, standardize it first, then come here and try to solve it with us. So let's say we want to evaluate this expression. And let's see the table here. Okay. So the table here have the values of z in the first column and in the first row. Where in the first column you have the first digit and the first digit after the decimal. And in the first row, you have the second digit after the decimal. You have to learn how to read this table and to get the values from it. So here's the thing. In order to evaluate this one, we need 2 conditions met. First of all, the value for small z here must be, the sign for it must be equal for the sign for the table. So here we are using the positive numbers table. As you can see here, all the numbers here are positive. I'm not talking about the probabilities. The probabilities are always going to be positive. I'm talking about the numbers in the first row and in the first column. Okay, so does the number match the number? Does the outcome match the sign of the table you are provided with? So here we have positive number and positive table. So this is the first condition met. The second condition that need to be met is the expression cumulative, because as we can see here are the cumulative standard deviation distribution. So all of these values you can see are cumulative values. So we need these two questions answered before we start solving. One, is the expression cumulative? Two, does the sign of the outcome match the sign of the table provided? In this case, both questions are answered yes. And with this, we can straightforward go and solve. So how to solve? Well, as we have said, the first two digits here, and the second digit after the decimal is above. So the first two digits is 1.6, so we find 1.6 here, and the last digit is 5, so we find 0.05. So it's this one. So it's going to be this row here and this column here. The intersection of them is going to be the answer that you are looking for, and here how we can evaluate this expression. Next one, the probability of z greater than 0.62. Let's ask our questions. The first question, is it cumulative? No. Does the number match the number does the sign of the outcome match the sign of the outcomes in the table or the z values? Yes. So the one question is unanswered. How can we fix this one? We just make it a cumulative expression. So how do we make it a cumulative expression? As easy as it is, using the complement rule or the complement method. So using the complement, and yes, now after we have had a cumulative expression, now we can evaluate it. How do we evaluate? The first digit and the first digit after the decimal, 0.6. So find 0.6 here. Here it is. There is 0.6. The last digit, 0.02. Look for it. It's there. So it's going to be like this. The intersection of them is this value here, and this is going to be the answer after you subtract the 1 from it. So 1 minus this value here, you're going to give you the answer. Next, the probability of z greater than or equal minus 0.34. Let's ask our questions. Is the expression cumulative? No, it is not. Does the sign of the outcome match the values of z, the signs of the values of z? No, it doesn't. So both questions are answered no. Well, do you remember how do we solve this one? Remember the property we talked about earlier in the visualizing slide. So we can use, instead of using this, we can just flip them around. And the reason behind it is in the graph here, look. So the first graph is for our original expression, where the value of z, or the probability of z greater than or equals minus 0.34 is the first one. And this one is the one below it. So with that symmetry property, we could solve this question here. And of course, go look for the first two digits, or the first digit and the one after the decimal, and the last digit, and you're going to get the intersection, which is going to be your answer. Now, Now, for this one, the probability of z less than or equal minus 1.01. Let's ask our questions. Is it cumulative? Yes, it is cumulative. Does the sign match the sign in the table? No. This is negative, and the numbers provided in the table are positive numbers. So the first question is answered, the second one is not. So how can we solve it? We can solve it over multiple steps. So the first step we do, we flip it using the first one here. You see this, what we have done here? We do that. Now, the sign of the number here is equivalent to the sign in the table, okay? After that, it becomes like just a problem like the one above here. We just take the complement of this one, and we're going to end up with an expression that we can evaluate that is both cumulative and the sign of it matches the signs we are given in the table. So evaluate it, 1.01, where is it? Yes, it's going to be this one. Yep. And we subtract 1 from it, of course, and we should end up with the answer here. Now, the next one, it looks a little bit convoluted, but remember, I have told you how to solve these expressions here. You take the cumulative of the second number here, the biggest number, and you subtract this, the cumulative of this number from it. So when we do this, we should end up with something that looks like this. Okay? This we can easily evaluate. This one we cannot easily evaluate. We have to deal with it like we have dealt with this case here. So deal with it as it is, and you should end up with this number at the end. Okay. The last one, we can use the properties of symmetry to solve this one. So we can take 1 minus 2 multiplied by the probability of this one here, and we can just do the properties on it and play with it until you end up with the answer here, until we make it an expression that we can evaluate. Okay. So that's it for the evaluation of normal distribution function or whatever it is. Now let's have a question from the book on evaluating normal distribution. Question says, use appendix table 3, which is a table we just have seen, to determine the following probabilities for the standard normal variable z. Standard normal variable already standardized. Well, we're going to be using the positive numbers table, and we have all of these expressions to evaluate. So the first one, ask yourself these two questions always. Is it cumulative? Yes, it is cumulative. Does the sign of the outcome matches the sign of the table? Yes. Positive, positive. You can right away go look for it in the table and evaluate it straightforward. And you should end up with this probability here. Next one, probability of z less than 3. The same two questions. Is it cumulative? Yes, you have less than. Is it positive? Does the sign here match the sign in the table? Yeah. Positive, positive. Perfect. You don't need to do anything, just go evaluate, just go look for the number in the table. Now, probability of capital Z greater than 1.45. Now, is it cumulative? No. Does the sign match the sign in the table? Yes, it does. So just use the complement method and make it into an expression where you can evaluate it, where it's cumulative and the sign matches. You're gonna go look for it forward in the table. I think there is an issue with this number. I did not maybe subtract 1 from it. I'm going to check it for you and upload the corrected slides, inshallah. Now, probability of z greater than minus 2.15. Okay. Is it cumulative? No, it is not. Does the sign of the outcome matches the sign of the table? No, this one is negative, this one is positive. So what do? We do the required procedures in order to be able to evaluate it, and after you do it, you can evaluate it right away. Now, the last one, we know how to deal with this one. We take the cumulative of the second and we subtract the cumulative of the first, or we take the cumulative of the biggest number and we subtract the cumulative of the smaller number from each other. Or you can get away with putting an absolute value like I'm doing here. You can just put an absolute value and get away with it because you are dealing with probabilities, because you always must get the numbers positive. Okay? So after you do this, you can see that this one you can evaluate, but this one you cannot. So you do further procedures on this one, and you should end up with an expression that you can evaluate and get the answer at the end. Okay, I'm gonna make sure of this entire slide if there is a mistake or not. Okay, I'm gonna upload the corrected slides, inshallah, for you. Now, more questions. Here are more questions for your practice. You can practice all of these as you see fit. Use them in your advantage. I'm gonna make sure of these ones, although I'm highly sure about these ones. Now, we're gonna find the probability for a certain z in normal distribution. Well, you might say, can't we already do that? You're giving us a z and we're trying to find the probability of it in the table, right? Yes, but there is a case that I'm gonna show you here. Let's say that you have this number. You might say, well, it's cumulative and the sign matches the sign in the table. We can still find the probability for it. What's the problem? The problem is the additional 3 here. Our z values go only for 1 digit here and 2 digits after the decimal place. Here we have 3. And in our table, we don't have 3. So how do we deal with this one? Well, we have 2 steps. Let me show you the table first, that you cannot really evaluate it straightforward. So there is no 0.243. There is 0.2 and there is 4, but there is no additional 3 next to the 4. So we cannot really evaluate it straightforward like that, even though it complies to both of our questions or conditions. So what do? We're going to use something called linear interpolation. We're going to see the formula later. Now, the first step we should do in this case, we look for the 2 surrounding numbers of this one. What do I mean? The 2 numbers that are present in the table that will enclose that number. How? So this is 0.243. The 2 numbers that will enclose it are 0.24 and 0.2 So 0.3 would exist between them. And both of these, we can find them in the table. This is the condition. We have to find these two numbers, but they are in the table. Now, after we have found them, now we need to find some variables. Where are these variables? Coming from this formula there. We have to find Z1, Z2, P1, P2, and one of these red ones. We're going to see depending on the question we have. So Z1 and Z1 and Z2 we have already found. Guess what? This is Z1 and this is Z2. Z1 is the smaller of these two numbers and Z2 is the bigger of these two numbers. So this is Z1, this is Z2. What is P1? P1 is the cumulative probability of Z1. Where is it? You can find it in the table. So this is the cumulative probability for Z1, 0.24, 0.24, intersection between them is this value here, and the cumulative of Z2 is 0.25. You can find it in the table there. So put the variables that you have, Z1 and its probability P1, Z2 and its probability P2, and you are given the red Z, but you are not given the red P. You are trying to find P. So trying to find P, this is going to be our majhul or whatever that is in the formula, and after you do the linear interpretation, you're gonna get the answer, inshallah. Here is a thing, I have put 0.25 here. It should be 0.243. It should be this number there, but I made a mistake. I apologize. So now we have found the value. We have found the P for a certain Z, but now what if we want to find the Z for a certain P? How? Let's say that we have this case. We have the probability of capital Z less than Z equals 0.8. So we want to find the value of Z such that will give us 0.8. Okay? The procedure is quite similar, but there is a slight difference at the beginning of it. So we're going to have the table, and we're going to have our first step, which is finding two closest points surrounding the probability points of this number. What do I mean by this? We want to find two probabilities in the table that will enclose this one here, 0.8. If we look in the table, we can see that 0.799564 and 0.802338 will have 0.8 between them. So these are the two probabilities I'm looking for. After I have found the probabilities, now I can find the Z1 and Z2. I have P1, which is this one. I have P2, which is that one. The intersection of these is going to be Z1. Intersection of the second one is going to be Z2. Let me show you. So these are the two probabilities. We have found them. We're going to find the variables. The first variable, which is 0.84, which is written here, is found like this. Found the intersection here between these two, and you end up with this probability. And the same for the second one. With this, we can put the variables that we need here. And we know the probability, the red P, but we don't know the red Z. So with this, we just put everything here, and hopefully we end up with the correct answer at the end. Yes, assume that Z, I'm going to solve, this is an example from the book regarding what we have just solved. Finding P from certain Z in normal distribution. So assuming Z has a standard distribution, use appendix table 3, which is a table, to determine the value of Z. That solves each of the following. Okay, we're going to use the positive numbers table in this question, and here is the following. The probability of capital Z less than small z equals 0.9. From the table, go find the two probabilities that will enclose 0.9. When you go to the table, you're going to see that the first number is going to be, the first probability is going to be this one, and the second probability is going to be this one. You go look for the numbers tied to these probabilities, or the Z values for these probabilities. You're going to find Z1 to be 1.28 and Z2 to be 1.29. And with this, you have the red P, but you don't have the Z. You are trying to find the Z. And at the end, you should get the Z to be equal this value. As you can see, the Z is between these values. So yeah, that's why we are looking for something that encloses it. It's between 1.28 and 1.29, like this. Okay, very good. Here are some examples for you to practice if you want, and I would recommend it because you're going to see this type of questions a lot in the book. Now, we're going to be solving some inclusive problems. See all of this mumbo jumbo that I was talking about, all of these ideas scattered all around. Now we're going to have some questions that will gather all of them, and hopefully we have a good foundation that we can rely on in solving these questions. Now, assume that capital X is normally distributed with mean of 10 and standard deviation of 2. Determine the following. So we're going to use now the negative numbers table, and here we have the mean and we have the standard deviation, as we always might need them. First part D. Yeah, I'm starting from part D. Probability of X from 2 to 4. The thing is, what is the first step that we always should do when we are solving these questions? We always first standardize. Is this standardized? No. Standardize it. After we standardize it, we should end up with this expression here. We know how to evaluate this expression. We take the cumulative of the biggest number minus the cumulative of the smallest number, and we should end up with this here, so we can evaluate it. By the way, we are using the negative numbers table. So when we look at this expression, it's cumulative, and the sign matches the sign in the table, which is the negative number, the one that we are using. Same goes for this one also. So finding this would be quite easy, straightforward in the table. The next one, probability of capital Z less than 13. Here is a thing that I have not explained. We assume that the normal distribution goes from -4 to 4. It actually goes from -infinity to infinity, but we assume that it goes from -4 to 4. So any value that is less than -4 that you are trying to find the cumulative of is going to be 0. So -5, cumulative for -5, 0. -6, 0. All of these below -4 are going to equal 0, the cumulative of them. And for 4, which is what we assume, it goes from -4 to 4, and everything, all the cumulative that are above 4, we assume that they are equal 1. So 10, the cumulative of 10 equals 1, the cumulative of 5 equals 1, the cumulative of 4 itself equals 1. So with this idea in mind, the cumulative of 14, how much it should equal? Should equal 1. So straightforward, you don't even need to go to the table because it does not exist in the table. The next one, same idea as this one. So we do the same procedure here. We standardize first, then we take the cumulative of the bigger number minus the cumulative of the smallest number. By the way, I'm putting the absolute value. I can get away with doing it. I have explained it before. So go look for these values straightforward from the table, and you should end up with this answer at the end. Now the last one, we standardize first, then we use one of the properties that we have seen in the previous table, in the previous slides, where we can use the symmetry property in order to find the probability to be like this, where we can just find one probability of -2 instead of finding this and then subtracting it from this and this, and you do procedures, all of this. You don't need to do all of this headache. You can use the properties of symmetry and you end up with the answer like this, inshallah. Now let's continue this question. This part of this question will ask us to determine the value for x. So we have all of these parts of the question. We need to find the value for x for each of these expressions there with the same parameters that we had earlier, and we're still using the negative numbers table. So with this in mind, let's go to the first question. The first question tells us find the probability for capital X greater than x equals 0.5. So we want to find the value for x that when we take this expression of it, when we take x greater than this value of x, will give us 0.5. So the first thing we do is to standardize. So how to standardize? Just put z's in here and it looks like you standardized something, although you barely did anything. But anyway, so we have to find this value of z that when we take whatever above it will give us 0.5. There is a thing. We don't need the table for that. We know that the shape is perfectly symmetrical around 0. And if you take the whatever half of 0 will give you 50%. So if, let's say you take from 0 above up to infinity, it's going to be 50%. You're going to take 0 down to minus infinity, it's going to be 50% also, which is 0.5. So the value for z here is going to be 0. Now we have found the value for z. What do we do after that? Now we do some sort of reverse standardization, something. So in standardization or in standardizing, you find the value for z, but now we're gonna find the value for x again. How do we do it? We do it algebraically. We bring the sigma here, multiplying it by the z, and we bring the mean or the mu to the other side positive. So we're gonna end up with this equation here that then we plug all the numbers we have, the mu, sigma, and the z, should end up with the answer here. Okay, quite simple. Now, the next one. The probability of capital X greater than X equals 0.95. The same idea here, but the value for X would definitely change because you are trying to find the value of X that you take everything above it, you're going to end up with 0.95. Standardize first. After you standardize, now we need to use the table. The thing is, if I'm going to use the table, I have to have clear number in front of me or what? No, not necessarily. The thing is, let's ask our two questions that we do whenever we are evaluating a normal expression. First one, is the expression cumulative? Well, we can clearly see it is not cumulative. Second question, does the outcome, the number for the outcome, matches the sign for the outcome, matches the sign of the table? So is the z negative and the table negative? Well, we know that the table is negative, but we don't know the z is negative. We're trying to find the z. So how do we know? Well, there is a simple trick that will allow you to know it. It's quite intuitive, but I'm going to say it. So if you take the cumulative for all of the negative values in the z table, so go look at the z table, none of these values is greater than 0.5. All of the cumulative values for the negative z numbers are less than 0.5. So now we're gonna ignore the z. Let's make this expression cumulative to begin with and see where we can go from there. So how to make it cumulative? We take its complement, we bring the 1 to the other side, we multiply by the negative 1, and we end up with this one. So the cumulative of this z that we are trying to find is less than 0.5 because it's 0.05, it's less than 0.5. With this, we know that it is less than what? It is less than 0, which is negative, this negative. So both conditions are met now. The expression is cumulative, and we know that the z is cumulative because we got from its cumulative probability a number that is less than 0.5. Go look for it in the table. Maybe your doctor is going to ask you to interpolate this one and find it using linear interpolation, finding a certain value, finding z for a certain value of p or something like this, the ones that we have solved. But maybe your doctor is going to be merciful and tell you, okay, go for in the table and look for the closest number to it, the closest z that will give you this number here. And when we do that, we find the value to be 1.64. So with this, we do this step again where we change the z into an x by using this formula here or this equation, and we will end up with this value. What does this value represent though? What does 13.28 have in meaning? Well, it means that 95% or 0.95 of the data we have in the normal distribution are above this one. It is exceeded by, this value is exceeded by 95% of the data we have. So this is it. Now to the last part of the question, which is the most difficult. What do? The first thing that we always do is to standardize. Just put the z's all over and it looks like you've standardized. Yeah, it's a good procedure. Now, after we've done this, we cannot really evaluate this thing. We have to change it into a thing that we are used to or thing that we can evaluate. And I'm gonna choose to do the last procedure that we have done in the slide of evaluating normal distribution. So we're gonna end up with this expression here, or this statement here, or whatever it is. I'm gonna put the probability expression in a side by itself and the probability in a side by itself, and we're gonna end up with this. The thing is, you might see the negative z and be a little bit confused here. You might say, okay, yes, it is cumulative. However, I don't know, z is multiplied by 0, it is negative, now it's positive. You might get confused by that. The thing is, ignore that the negative sign exists whatsoever and evaluate this one. So what is the value that you're going to see in the table that is closest to this one? Or maybe your doctor wants interpolation. Allah ya'eenak out. So in this, if we go look for it in the table, it's going to be minus 1.96. But remember, the thing we have found is a minus z, not z. So in order to make it a z, we multiply it by -1 both sides, and we end up with the true value for z that we are looking for. Now, after we have done this, we're not done. We have to do this step. But here is a small difference. Instead of having an x here and we put the x here, now we have x minus 10. So we're going to put x minus 10 here, and put the formula, the rest of the formula as it is. So now we plug in the numbers, and we should end up with the final answer equaling 3.92. I'm sorry, I cannot remove this thing. If I press the x, the entire thing shuts down. So I'm sorry, I don't know how to deal with it, but it's 3.92. And this is an example for you to practice at home if you would like. Okay, finally. Now, to the actual part of the, not to the actual part, now to the actual conceptual questions, the things that you might expect to get in an exam. So, this is conceptual question in the normal distribution that says, the time until recharge for a battery in a laptop computer under common conditions is normally distributed with a mean of 260 minutes and a standard deviation of 50 minutes. So, we are given the mean, we are given the standard deviation, and the question just clearly tells us that it follows a normal distribution. We're always going to see this in normal distribution, or at least I have not seen a normal distribution question that did not put this statement as clearly as it is here. So let's see the first part of the question. Of course, we're going to use the negative numbers table here. What is the probability that a battery lasts more than 4 hours? As we can see here it asks the battery lasting more than 4 hours, but here we have the mean and standard deviation in minutes. So you either change everything to minutes or everything to hours. I chose to change everything to hours. So with this, the expression that we need to solve is probability of x greater more than 4 hours, greater than 4. So this is the expression we're going to be solving here. So the first step we should do is to standardize. After we standardize, we should end up with this expression here that we can solve easily. And we do some of these procedures, some of the that we've seen in these previous cases, and we should end up with the answer here at last. Okay. The next part of the question. What are the quartiles of battery life? He's asking about the first quartile, which is the 25th percentile, and the third quartile, the 75th. Okay, what are quartiles? Let's get a refresher. What are quartiles? Quartiles are the values at which, the first quartile I'm talking about here. The first quartile is the value at which 25% of the data is below it. So is it safe to write it like this? Yes, since it is the value, small x is x is going to be the quartile, the value for the quartile, and it has 0.25 of the data below it, so it's safe to write it like this. With this, now we standardize it. After we standardize it, now we can evaluate it. As we know, this expression is cumulative, and the z is negative. Why? Because this is 0.25, which is less than 0.5, and as we know, the cumulative for whatever negative number we have is always less than 0.5. Okay? We go look for it in the table. We get this value for z, and we do the reverse standardization thing. We should end up with the answer here, which is the first quartile, or Q1 if you wish. Now, the 75th percentile, or the third quartile. The same idea, the third quartile has 75% of the data below it, so it's safe to write it like this. We standardize it, but here we have a problem. Yes, it is cumulative, however, the value for z, it is not negative, so how can we solve it? Well, the thing is, we apply the cases that we have already learned in the couple of previous slides, where you have the expression being cumulative, however, the sign of the z does not match the sign we are provided with in the data, or in the table. So we do these procedures, and we should end up with the value be equaling this one here. Do the reverse, standardization thing, find the x, and this is your answer at the end. Now with the last part of the question, what value of life in minutes is exceeded with 95% probability? So what they're asking for is the value of x such that it has 95% of the data above it. See, it is exceeded with 95% probability. 95% of the data is above it. So it is from what? From the bottom 5%. So if I try to find it, I can write the expression like this. The probability for capital X less than X from the 5% is equal 5% or 0.05. How do we solve this one? We've seen how to solve it. We standardize, we find the value for Z, we do the reverse standardization thing, and we end up with the answer at last. Now, the next question. A driver's reaction time to visual stimulus is normally distributed with mean 0.4, we have the mean, and standard deviation of 0.05, we have the standard deviation. Let's see the first part of the question. What is the probability that a reaction requires more than 0.5 seconds? So the probability of a reaction requiring more than 0.5 seconds, so the probability of X being greater than 0.5. So we have to solve this one. How to solve it? First, we standardize. After we standardize, we have this expression that we should be able to solve. Now, if we solve it, we should get this probability at the end, inshallah. Next part. What is the probability that a reaction requires between 0.4 and 0.5 seconds? Okay, so just playing with the ranges here. The expression would look like this. You would just have to standardize it first, and we have solved this one about 1,000 times now. So we should end up with this answer at last at the end. I think this is the last part of the question. What reaction time is exceeded with 90% of the time? Is exceeded 90% of the time. Okay. So remember that was 95, exceeded 95. Now it's exceeded 90%. What they are asking for is the value of X such that have 90% of the data above it. So it is from what? From the bottom 10%. So we are trying to find the bottom 10%. So how to find them? Using this expression here, bottom 10%, 0.1. Standardize it first, then find the value for Z, do the reverse standardization, you should end up with the answer at last. Now we're going to learn how to approximate binomial using normal distribution. So maybe the problem in binomial will become too difficult or too long to solve by hand. Maybe you have 1,000 things that you need to add, and even using the complement method is not going to help you. So in this case, you may want to approximate the binomial using normal distribution. Well, when can I do that though? I would assume that I cannot do that all the time. Yes, there are some conditions that need to be met in order for you to be able to use this approximation, which is that NP would be greater than 5 and N1 minus P would be also greater than 5. In this condition, in this case, you can approximate binomial using normal distribution. Well, how can I do that? Well, you can do it using these two horrendously looking expressions, but they have a simple logic that we are all used to. The thing is, you have X here subtracted by the mean of the binomial divided by its standard deviation. So it's nothing except for standardization. It's standardizing the binomial using its mean and its standard deviation. However, we have here the 0.5. What does the 0.5 represent? It is just a correction factor that when you have the expression to be less than or equal, you should add it. And if the expression is greater than or equal, you should subtract it. You can remember it as it is. But the thing is, the expression must be equal. So we're going to see some cases where it won't be equal and we need to make it equal because here we're approximating binomial, and binomial is discrete and the equal sign matters in the discrete. Now we're going to solve a question about normal approximation of binomial. So the question says, among homeowners in a metropolitan area, 75% of them recycle plastic bottles each week. A waste management company services 1,500 homeowners. Approximate the following probabilities. Let's see the first part of the question. At least 1,150 recycle plastic bottles in a week. Here's the thing. This question is a binomial question. Is written as a binomial. It is a binomial question. The thing is, and the thing that might give you an indicator that you might need to approximate, use the normal distribution, is the word approximate. So when you see this word, this could be an indicator for you that you must use normal approximation. So With this part of the question asking us to find the probability of at least 1,150 owners recycling plastic bottles in a week, this is going to be the number of successes. I'm not going to go too deep into the binomial distribution, but this is going to be the expression that we're going to try to solve. And let's see the formula that we're going to use in order to solve this thing. So the formula says x, which is the outcome, which is this one here, minus NP. Well, we should know what N is 1,500, and P is the probability of somebody recycling, which is the mean of the binomial distribution over the standard deviation. So let's find all of them here. Well, good. Well, and here we're going to also subtract by the correction factor, which is minus 0.5, because here we are dealing with greater than or equal, and we subtract when we have greater than or equal. With all of this, now we can solve this question, and we get the answer at the end. Instead of, I don't know, dealing with 1,500, I don't know how many expressions you're going to add when you solve this one using hand. The next part of the question, between 1,075 and 1,175 recycled plastic bottles a week. So they're just playing with the range. Our expression that we need to solve is going to look like this. Here's the thing. We're going to put the formulas here. Can I implement the formula? Can I use the formulas on this expression? No. For the reason that these inequalities should have an equal sign. See, as we can see here, this probability of z less than or equal, and this probability of z greater than or equal. Here we have only less than, we have greater than. So how can we fix this problem? It's very simple. So let's ignore this part to begin with and only deal with this one here. So what is less than, so x less than 1,175, what is less than this one by one increment? It is 1,174. For this one, you can, I don't know how to hide it, but for this one, it's going to be x greater than this number. What is greater than this number by one increment? It's going to be 1,076. So now we're going to be able to use these formulas, and after we use them, we standardize, and we should end up with this one, which we can solve using this method here, or this way of implementing, and this is the answer here at the end. Earlier, we have learned how to approximate binomial using normal distribution. We can do the exact same thing for the Poisson distribution, where we can approximate it using the normal distribution. But when can we do it? We can do it when we have lambda to be greater than 5. How can we do it? We can do it when by using these two expressions which have the same exact logic that we have done with the binomial, where you are subtracting the mean of the Poisson and dividing by the standard deviation for the Poisson, and adding the correction factor when you have less than or equal, and subtracting it when you have greater than or equal. Now let's have a question. The question says, hits to a high volume website are assumed to be to follow a Poisson distribution with mean of 10,000 per day, 10,000 hits per day. Approximate, see, approximate each of the following. Okay, let's see the part of the question. Probability of more than 20,000 hits a day. Okay, so we need to evaluate this expression here, where we have probability of x greater than 20,000, more than 20,000 hits in a day. Let's see our formula here. Okay, our formula though only works when we have greater than or equal. But before we deal with this, let's find lambda. What is the lambda here? The lambda in question is 10,000, so let's put lambda aside. Now let's fix this issue here. So we need to have greater than or equal. How do we do it? We do it just simply by adding 1, because greater than 2,000, greater than 20,000 means just 20,001 and above. So there's some sort of logic behind it in that case. It's quite easy. So after we got the expression suitable for our approximation, now we can just implement the approximation right away and get the answer at the end to equal 0. The next part of the question, probability of less than 9,900 hits in a day. Okay, so this is the expression we're going to solve, less than 9,900, and we're going to use this formula here, since we have less than, we're going to have this formula that have less than or equal, but we need to change one thing about this, make it less than or equal by, you know, subtracting 1 and having the equal sign here. So just implement the formula right away and you're going to get the answer at the end. Oh, I did not put this one. I'm going to put it in the slide. I'm not going to redo the shot. The next distribution we're going to be talking about is the exponential distribution. So this distribution, you can imagine it as being some sort of a geometric distribution for continuous random variable. In the geometric distribution, we have to find the first success in X number of trials. This exponential distribution will also try to find the first success in a given time or in a given value or given measurement, maybe not only time, maybe length, maybe area, but it tries to find the first success in that. So the probability mass function has the rate or lambda as the only parameter here, which denotes, as I have mentioned, the rate, domain of x going from 0 up to infinity, and the cumulative distribution function is this one, which is the only function that I'm going to be using to solve the exponential distribution. The mean, and of course, as I have mentioned, it is similar to the geometric distribution. That's why it has the lack of memory. Here is the function or the idea of lack of memory written as an equation or as an expression here. And the formula for the mean and the formula also for the variance. Before I go to explanation, the mean is, understanding the mean is quite crucial, and differentiating between the mean and the rate is definitely crucial, because you need the rate, which is lambda, to solve the question. But sometimes in the question they play a trick on you and they give you the rate, the mean instead of the rate. They give you this one, 1 over lambda, while you actually need lambda. As you can see here, you're gonna solve using lambda. So in the next slide we're gonna see how can we differentiate between them both. So examples of lambda are gonna come like this. They come as rate of successes per unit. Here 10 calls per hour. Maybe you have flow per square foot. It's not flow, it's flaw, or maybe flow. It could be, both could be. But you know, you understand it. It's a rate of success or a rate of success per a given unit. So failure per hour and cars per minute. Lastly, counts per minute. Where 1 over lambda, or the mean of the exponential, here's the thing, refresher, this is the mean for the Poisson, this is the mean for the exponential, and we are solving for the exponential here. So examples of it might be time between calls is 15 minutes. Okay, there is no rate, there is no per in this. And here's the thing, this has nothing to do with this. Okay, just ignore them. They are not like we have translated them into 1 over lambda. No, these are different examples, and these are different examples. So next one would be time between arrival with mean of 10 minutes. Okay, or maybe the distance between cracks in a highway with mean of 5 minutes. Here 1 over lambda is 15, 1 over lambda here is 10, and here is 5. Of course, if you want to find lambda, you have to get the reciprocal. Last one, we have the mean of a mechanical assembly. This is going to be 400 hours, a lifetime of mechanical assembly with mean of 400 hours. Now, let's solve a simple question. Suppose that capital X has an exponential distribution with lambda equal to, determine the following. We need the formula, so I put it there. So solve this one. By the way, this formula is for the exponential, as you can see, capital F of X. So whatever you're going to be solving here should be translated or should be transformed into an exponential expression before you start applying the formula. So here, probability of capital X less than or equal 0, or the cumulative probability of 0, just X given, lambda given, implement everything, you're going to get the answer at the end. Next one, probability of capital X greater than or equal to. This is not cumulative, make it cumulative. Now you have X, lambda is given in the question, solve the question right away. Next one, probability of X from 1 to 2. Remember the way we have solved the normal distribution, we're going to still utilize the same idea, where we take the cumulative of this one, we subtract it from the cumulative of this one, and we should end up with the answer looking like that. Here, yes. Last one, probability of capital X less than or equal 1. There is nothing tricky about it. Same idea. Get the you have the x and you have lambda. Implement the formula right away. Now, next question. Find the value of x such that p, the probability of capital X less than x equals 0.05. We have solved many questions that look like this. What do they want from us is to find the value for x that would give us this probability for this expression. This expression is cumulative, so we can use the cumulative function on it, and it would look like this here. It's gonna look like this, where x we have substituted using x, and now we're gonna solve for x, and after solving we should end up with this answer here, inshallah. Now with an actual question for the exponential distribution. The question says, the lifetime of a mechanical assembly in a vibration test is exponentially distributed with mean of 400 hours. Bear in mind, they gave us the mean here. The mean of what? The mean of the test that follows the exponential distribution. We know the mean for the exponential distribution is 1 over lambda. So 1 over lambda equals 400. But we don't need 1 over lambda here. We need lambda. How do we find it? Get the reciprocal. It's going to be 1 over 400. Okay. With this out of the way, let's see the first part of the question. What is the probability that an assembly on test fails in less than 100 hours? Okay. So we want to have our first failure in less than 100 hours. Okay. So the probability for x being less than 100, and the rate of failure is given to us, which is lambda, and of course it's given in hours too, bear in mind, and we can use the formula there, the cumulative, to solve this question. Since the expression is cumulative here, we should end up with this answer here at last. Next part. What is the probability that an assembly operates for more than 500 hours before failure? So here, the same idea behind everything. However, they have just changed this part of the question, where instead of asking about it failing in less than 100, now they are asking about it failing after it operates for more than 500 hours. So we want our first failure coming after 500 hours. So probability of x is going to be x, probability of x greater than 500 is what we are trying to find. It's not cumulative. We need cumulative, so we can solve it using that equation there. After we change it to cumulative, we can solve it right away. Nice. Next one. If an assembly has been on test for 400 hours without failure, okay, what is the probability of failure in the next 100 hours? Okay, so they have told us here that the assembly have been going on test, and the first 400 hours it has not failed there. Okay, we want to find the probability of it failing in the next 100 hours. Okay, so here's the thing. We have lack of memory here. And remember, lack of memory does not care about what already happened, that we know its results. Well, they told us that the first 400 hours gone without failure. Well, I don't care. I care about the coming 100 hours. So the coming 100 hours are gonna be expressed like this: probability of x less than 100, so which is the probability of them failing in the next 100 hours. Maybe it fails in the next 5 minutes, maybe it fails after 25 hours, maybe it fails at the 100 hours exact. Who cares? But we don't care about the previous 400 hours. Lack of memory. Now solve it right away. So we already solved this one, right? Yeah, we already did. I don't mean solve the same part. We solved the probability of x less than 100. Now, next part of the question. If 10 assemblies are tested, what is the probability that at least one fails in less than 100 hours? Assume the assemblies fail independently. Okay, this question is a handful. Let's reread it. We have 10 assemblies being tested here. They are asking for the probability that at least one of these 10 assemblies fail in less than 100 hours, whatever. This question has some binomial in it, right? Yeah, actually it is. Part of it is binomial and the other part of it is exponential. The binomial part of it is asking us to have 10 assemblies, which is a discrete number of assemblies, which is a discrete value, the number of assemblies, at least one of them failing. So we are trying to find for the number of failures, or our outcome of interest here, in less than 100 hours. So for this binomial distribution, we know n, we know that we have 10 assemblies, and we know the number of successes we want to have, at least one, x greater than or equal 1. However, what is our probability of success? Our probability of success is finding the probability that one of these machines fail in less than 100 hours. And we know that the lifetime of these machines is modeled using exponential distribution. Okay, so once we found the probability that one of them fail, which is modeled by exponential distribution, now we have the probability of our outcome of interest, which is going to be solved using the binomial. Here, the probability of our outcome of interest. We're trying to find at least one success here, and take the complement and everything. You're going to get the answer at the end. The next part. If 10 assemblies, actually this one is for you to try. So the answer for it is already laid for you here. If you want to try it, you want to check yourself whether you understand it or not, it is for you. The next distribution we're going to be talking about is Erlang distribution. The Erlang distribution follows a Poisson process. That's why we can solve it using a Poisson distribution or Poisson random variable. Why would we want to do that? Well, look at the formula. Have a look at the formulas and see why would we want to do that. So this is the first formula where we have lambda as the rate and r is the number of successes. Successes, but r can only take whole numbers. So 1, 2, 3, 4, 5. It cannot take decimals. Okay, and the domain of x goes from x up to infinity. Here is the cumulative distribution function, and this would show you nicely why we don't favor using it. We prefer to use the Poisson distribution to solve it. And here is the mean and the variance. We're going to use these. There is no problem with them. They're good. So the Erlang distribution, let's solve the first question. Raw materials are studied for contamination. Suppose that the number of particles of contamination per pound of material is Poisson random variable with mean of 0.01 particle per pound. Okay. It is a thing. It's a mean of a Poisson random variable. If it told you it was the mean of an exponential random variable, then this is going to be 1 over lambda. But in this case, it's the mean for Poisson random variable, and we know the mean for Poisson is what? It is lambda. So there is no problem with the number we have. We're going to take it as it is. So what is the expected number of pounds of material required to obtain 15 particles of contamination? So 15 particles are the number of successes. This is our R that we need to use in order to find the expected number. Expected number, of course, we need to find the expected value, and here are the parameters that we are going to use, where R is the successes and lambda is the rate, lambda there, and at the end this is going to be the number of pounds of material required. Next part of the question is going to be, what is the standard deviation of the pound of materials required to obtain 15 particles of contamination? Same numbers, but now we're going to use different formula, the one for the variance, and then from it we're going to find the standard deviation. Here are the parameters, the same as they are, and here is the answer. Found the variance first, then we found the standard deviation. So the next question for the Erlang distribution is, the time between arrivals of customers at an automatic teller machine is exponential random variable with mean of 5 minutes. Okay. What is the probability that more than 3 customers arrive in 10 minutes? So here is the thing. You can say that the Erlang distribution is quite similar in concept to the negative binomial, where it gives you a number of successes and it asks you for the probability of this number of successes occurring in a given number of trials. Here we don't really have trials because we have continuous random variable, but you can account for the minutes to be like somewhat of a trial, where the 3 customers arriving are the numbers of successes you're looking for. It's somewhat like this. However, we're going to be solving this Erlang distribution question using the Poisson distribution. And in order to solve using the Poisson distribution, we need to find lambda. So what is lambda in this question? Well, lambda is in this question is the time between arrivals is an exponential random variable with a mean of 5 minutes. So we are given the mean of the exponential random variable. What is the mean for the exponential random variable? It's 1 over lambda. What is 1 over, and we want lambda, what do? We get the reciprocal. So 1 over lambda is 5 minutes. The reciprocal of it, 1 over 5 arrivals per minute. Okay, now think of it as a Poisson question. So in the Poisson question, the first thing you want to do to make sure that the unit of your lambda matches the unit that are asked for in the question, that your rate matches the rate in the question. So here we have 1.5 per 1 minute. We need to change it to whatever number per 10 minutes. So what do? Multiply by 10. We get the modified rate here, 2 arrivals per 10 minutes. Okay. Now, we solve it like it's a Poisson question. So the Poisson question tells us what's the probability that more than 3 customers, so we want more than 3 customers, these are the number of successes we are looking for. So the probability of n, I'm going to call the Poisson random variable n, greater than 3. We want more than 3 customers, greater than 4. Okay? So this is going to be, of course, we're going to make it, of course, Poisson distribution, you can, it's the domain of Xcode up to infinity, so we need to do all of these modifications. We already took Poisson distribution. Why am I explaining it? Here is the answer for it at the end. What is the probability that the time until the 5th customer arrives is less than 15 minutes? Okay. Okay. Modify the rate. Here we have the rate to be 15 minutes. Modified. Here we have it in 1 over per 1 minute. Multiply it by 15. You're going to get the rate, the modified rate to be 3 arrivals per 15 minutes. Okay. This is out of the way. Now, they want to find the probability that the time until the 5th customer arrives is less than 15 minutes. So in 15 minutes, we want 5, in less than 15 minutes, I'm sorry, in less than 15 minutes, we want either 5 or more customers, appearing or arriving. So what do? We try to find the probability of success being greater than or equal 5. So if 6 customers arrives, it is good. If 7 is good, if 8 is good, as long as it is 5 customers until it's more than 5 customers arriving in less than 15 minutes. So this is going to be our answer at the end, inshallah. This one. Next distribution we're going to have is the gamma distribution. The gamma distribution, you can call it as a generalization for the Erlang distribution, where in the Erlang distribution, you can only have R to be a whole number. It can be 1, 2, 3, 4, 5, 6, 7, 8. But here you can have R to be fraction. You can have R to be 3.8, for example, or the number of successes to be 6.5 or 6.78, whatever you would like. So you can say it's a generalization for the Erlang distribution. And the gamma distribution have something called the gamma function, which is in itself also a generalization for the factorial function. Remember, factorial, we know the factorial values for 1, 2, 3, 4. You can find 5 factorial, 6 factorial, but you don't you wouldn't be able necessarily to find 2.3 factorial or 6.5. This function help you to find these factorials with decimal places in them. Okay, the probability density function, here it is. We're not going to use it, but it's worth mentioning that it has a gamma function inside of it. Okay, what we're going to focus on here, we're going to focus on the gamma functions and how can we solve questions related to the gamma function using these properties. I'm going to go over each and every one of them. So the first one telling you whatever number you have here, you can subtract it by 1 and take it out, multiply it by the gamma function, and it stays here. An example of this, maybe you have R to be 3. You can subtract 1 from it. It's going to be 2. Multiply it by the gamma function that it's now become gamma of 2. Okay? The next one. It tells you that if R is a whole number, it's 1, 2, 3, 4, 5, 6, 7, 8, whatever. A whole number. Okay? If it's a whole number, you can subtract it by 1 and take its factorial right away. If it's a whole number, if it has a decimal, you can't. You can't do this one. Okay? Next one. Gamma of 1 equals 0 factorial, which equals 1. This goes without saying, just follows the one above here. Last one we have is when gamma equals half, it equals to the square root of pi, which I don't know where this came from, but it is there, use it. At last, we're going to have the mean and variance, which is the same formulas for the mean and variance for the Erlang, but here, remember, R is not always a whole number, can take whatever value, as long as it's not negative. I don't think it can take negative values. Now let's solve a question about the gamma function, and let's see how we can use its properties. So let's go with the first question. The first question tells us gamma of 6, and we know that one of the properties, if we have a whole number inside of the gamma function, we can do what? We can subtract it by 1 and take its factorial, which is the second property there. So as easy as it goes. Next one, gamma of 5 over 2. When I have a fraction over 2 like this, I like to convert it into decimal. So when we convert it into decimal, it's going to be gamma of 2.5. So this one, we're going to use the first property on it. We're going to get this number here. We still can do more iteration on it. We still can do more operations on it. We can still do the same the first property. When we do it again, we're going to end up with this expression. At last, we're going to end up with half inside of the gamma function. We're going to use the last property there in order to finish everything. And here we have evaluated this gamma function. Now, gamma of 9 over 2. So convert it into decimal and use the first property. Use it again and use it again. Oh, okay. Use it again. And of course, oh yeah, we have already found gamma of 2.5 here. Yes, we have already found gamma of 2.5 here. So, you know, we already know its value. Multiply it by these numbers and you're going to get the answer at the end, inshallah. The last distribution we're going to have is the Weibull distribution. So for the PDF, we're going to have two parameters, beta and delta, where beta is the scale parameter and delta is the shape parameter. Both of them only take non-negative values, with the domain of x going from x up to infinity. The cumulative distribution function, which is the one that we are going to use in our solving, looks like this. The mean and the variance, these are the formulas for them. They have a gamma function in them, so by now we should know how to evaluate a gamma function. So the first question, suppose that capital X has a Weibull distribution with beta equal 0.2, delta equal 100. Determine the following. Okay, so of course we're going to put the formula there because we're going to need it. Let's see the question. They're very easy questions. So the first question, probability of capital X less than 10,000. It's a cumulative expression, so we can right away implement the formula with X equal 10,000. Delta is 100 and beta is 0.2, and we get the answer at the end. Next one, it's not cumulative, but we can make it cumulative by taking the complement. 1 minus the complement is going to equal the answer, this answer at the end. So, next question, probability of X greater than 6,000 given that X is greater than 3,000. So, what is the probability that, I don't know, X gonna be greater than 6,000, given that already 3,000 hours have passed, or 3,000 of whatever measurement is of this has passed. So to solve this, we need to have the conditional. We need to know the conditional equation. So when you have probability of event A given event B, you take the intersection of them, you divide them by the given event. So what is the intersection between these guys? So you have X going from 3,000 and then the other X going from 6,000. So the intersection between them is going to be from 6,000 up to infinity. Okay, so X greater than 6,000 is the intersection between them. And this one is going to be, we're going to put it in the denominator right away because, you know, it's the given one. With this one, we cannot evaluate each of them. At least using the cumulative, we have to, with the CDF, the cumulative distribution function, so make them cumulative expressions and solve them at the end. Now, after we have finished everything, now we're going to solve some supplemental exercises. The first question we're going to have is, suppose that the counters recorded by a Geiger counter follow a Poisson process with an average of 2 counts per minute. No problem. First part of the question, what is the probability that the first count occurs in less than 10 seconds? Again, the first count. What distribution did we take today that cares about first? I don't know, whatever, within a given time frame. It's the exponential distribution. So this question follows exponential distribution. So for the exponential distribution, we're going to use it using this formula, and what we're going to need is lambda. What is lambda here? Lambda is 2 counts per minute. So our lambda is going to equal 2. However, here in the question, they are asking about the probability that the first count occurs in less than 10 seconds. So we either make our lambda in seconds, or we make this, or the x, or this one here, make it in minutes. So I chose to make this one in minutes divided by 60. You're going to end up with the probability of x less than 1/6. Okay, because you want the first error to occur in, or the first count to occur in less than this time. Okay, so yes, use the formula right away and you're going to get the answer. Next part of the question. What's the probability that there are no counts in a 30-second interval? So, in another way, what I can say, what's the probability that we get our first count after 30 seconds? Both are the same way of saying the question. So, this question is also modeled using exponential distribution. So, instead of having the first, instead of in the previous question, we asked if the count gonna come in less than 10 seconds. Now we're gonna ask for the count to come in more than 30 seconds, because we don't want anything before 30 seconds. So here's the formula for us, and here is lambda, and this is in seconds. We have to change it to minutes. So it's gonna look like this, where we want to have our first success in more than 0.5 minutes or 30 seconds. Solve the question, you're going to get the answer at the end. Now, suppose that the count, it's the same question. Okay, next part. What is the probability that the first count occurs between 1 and 2 minutes after startup? They are just playing with the ranges. Between 1 and 2 minutes. So our, of course, we're going to need all of this, but our expression is going to be between 1 and 2. So not much tricks, and we know how to evaluate this one. It's very easy, and this is the answer at the end. Next question. The time it takes a cell to divide, called mitosis, is normally distributed with an average time of 1 hour and a standard deviation of 5 minutes. Okay, normally distributed. So this question follows a normal distribution. Let's see the parts of the questions. Of course, put the parameters there because we're going to need them. What's the probability that a cell divides in less than 45 minutes? So the probability of the cell dividing in less than 45 minutes, probability of x less than 45. In normal distribution, what do? We standardize, and when we standardize, we end up with this one. So we can easily look for it and solve it in the table. Next one. What is the probability that it takes the cell more than 65 minutes to divide? Probability of x greater than 65. Standardize, solve, you're going to get this answer at the end, inshallah. Okay, next part. What is the time by what time have approximately 99% of all cells completed mitosis? So we want the value of x, the time, such that 90% of our cells have already finished mitosis. Okay, so how do we find this one? It's going to be by using this one. So we want to find the value that's going to have success, that all already have completed mitosis. By 99% of them have completed mitosis. So we just evaluate this expression, and we have learned how we do it. We standardize and we find the value of x. We do, and then we do the reverse standardization thing where we try to find the value for x, and this is going to be the time required. The next question we're going to be solving is the percentage of people exposed to bacteria who become ill is 20%. Assume that people are independent, and assume that 1,000 people are exposed to this bacteria. Approximate each of the following. So this question is a binomial question. However, we need to approximate it using what? Normal distribution, of course. So with this in mind, let's read the other part of the question. Probability that more than 225 become ill. Okay, so the probability that x is greater than 225. However, this does not have an equal sign here. So we need to deal with this problem. How? we just increase it by one increment like this, so we can use that formula there. So this formula has NP, which is the mean for the binomial, over the standard deviation of the binomial. Let's find each one of them. The mean is going to be 200, standard deviation 160. Now just standardize and solve as a normal distribution, and this should be your answer, at least. That's what I think. Probability that between 175 and 225 become L. So this is going to be our range or our outcomes from 175 to 225. However, we need to have equal sign here and equal sign here. We have solved an example like this before. It's going to look like this. So now we can implement both formulas, standardize, and you're going to get the answer at the end. Now, the CPU of a personal computer has a lifetime that is exponentially distributed with mean life of 6 years. You have owned it for 3 years. Here it says exponentially, so it falls on exponential distribution. You have owned it, the CPU, for 3 years. Well, you have owned it for 3 years and it's still working, so we don't care. So this is lack of memory in the question. So we're gonna need the formula for the what is it called, for the exponential, and of course we are given in the question the mean life of the CPU. So the mean in the exponential is 1 over lambda, as we can see here, and the mean is this one, but we don't want the mean, we want lambda, so get the reciprocal. 1 over 6 fails per year. So what's the probability that the CPU fails in the next 3 years? So probability of X fails in the next 3 years less than or equal 3. So it's gonna fail in the next 3 years. I don't want it to fail more after. I want to know what's the probability of it failing in the next 3 years. So 3 years or less. I should maybe have put 3x less than or equal 3 here to be more accurate, but it still give the same answer. Ask your doctor if it's accurate or not, I don't know. So this is the answer here. The next part of the question is going to be assume that your corporation has owned 10 CPUs for 3 years. Okay, and assume that CPUs fail independently. What's the probability that at least one fail within the next 3 years? Remember this? We solved a question like this before, and this question is binomial mixed into exponential, where in binomial we know the number of trials here is 10, and we know the number of successes. We want the probability of at least one fail, which is our outcome of interest or successes. So x greater than or equal 1, but the probability is the one that we don't know, and the probability is of it. We want to find the probability of one failing within the next 3 years, which we have already solved in the previous part of the question. So the exponential part we have already solved, and this is the probability of it, which gonna translate to be the probability of success in the binomial distribution. Solving the binomial distribution will result into that answer there, 0.9933. Hopefully, at least. The next question is this one, which is quite long. I'm not gonna read all of it. I'm gonna crop the part that I care about. You should read it all. You should read all of it if you don't know it, but I know what's important in it. And what's important in it says that a Weibull distribution can be used to model web page dwell time. Dwell time is the time people spend in a page or web page. For specific web page, the shape and scale parameters are 1 and 300 seconds respectively. Determine the following. Okay, so we're gonna use Weibull distribution, and we have to determine the mean and variance of dwell time. We have to have the formula for the mean and the formula for the variance. We have to put our parameters, where 300 is gonna be delta, which is the scale parameter, and beta to equal 1, which is the shape parameter. So with this, solve for the expected value. The expected value is gonna be like this, 300 multiplied by gamma of 1 plus 1, which is going to be 2. Solve it, you're going to end up with 300 seconds as the expected value. And the variance is going to be this long solution here, and going to end up with this answer at the end. Next one. Probability that a web user spends more than 4 minutes on this web page. Okay, probability that spends more than 4 minutes in the web page. So probability of X greater than 240, we have changed the 4 minutes into seconds because the parameters we are given here are in seconds. So bear in mind, you can change them into minutes, or you can change this one into seconds. I chose to change this one into seconds. So with this, we can easily solve using the CDF for the Weibull distribution. Of course, after we make this one into cumulative, we should end up with this answer at the end. So with the last question, dwell time exceeded with probability of 0.25. So we want the dwell time, the value of x that we don't know, such that it's exceeded by 0.25 of all values. So it has 25% of the data above it, but 75 of the data below it. So we can say it's the probability of capital X less than small x equals 0.75. So with this, we can solve it, solve for x here, and after we solve for x, we should end up with this answer here. And with this, we have concluded chapter 4. If I had any mistakes in the slides, I keep repeating that, please tell me, because I make these slides myself and I don't have a solution manual that is updated so I can know the answers for these questions. So please help me with them. Thank you so much. Fi aman Allah.